I'm here at Future Food Tech in San Francisco, where I'm joined by the co-founder of Prolific Machines, a startup that is harnessing light-sensitive proteins that are used to control cells in biomanufacturing. Rather than controlling cell function by adding, pricey components such as growth factors to cell culture media, you're exposing cells containing light-sensitive proteins to light at these specific wavelengths. How new is this?
It's pretty new. So optogenetics as a field existed prior to Prolific, and light-sensitive proteins existed prior to humans.
Yes.
So there was billions of years of R&D prior to humans existing, which is a good thing. So the real inventors of this are cyanobacteria, and then the early adopters were plants and algae. But as a consequence, these proteins are everywhere.
Yes.
And they work really robustly because they've had billions of years to get fine-tuned. And then when humans started using them, the early applications were all in neuroscience. So people created light-sensitive ion channels and put them into neurons, and then used those to control the behavior of animals. And so there was quite a rich body of research on controlling animal behavior using light. But when I started Prolific, there was no company that was using optogenetics for manufacturing applications, which I was very surprised about, because it seems like, seemed at least to me like an excellent input into a manufacturing process, because it's extremely cheap, extremely easy to control on the time axis and the space axis, very reproducible, inherently sterile, inherently amenable to closed-loop optimization. So it seemed like we should be doing this in a manufacturing context, and that led me to start Prolific.
So you said obviously light-sensitive proteins have been around forever, but do the cells that are used by biomanufacturing companies naturally contain these proteins, or do you have to introduce them to the cells, and how do you do that?
That's a great question.
Yeah.
It's really important that they actually don't contain naturally occurring light-sensitive proteins, because the whole beauty of the system that we've built is that you can perturb one part of it without perturbing the entire system. This is very different to traditional biomanufacturing perturbations, where you'll do a pH shift, or you'll do a temperature shift, or you'll add a molecule. In all of those cases, those things perturb the entire system. And perturbing the entire system leads to a lack of control. So that's kind of what Prolific does. It's like, instead of changing the entire system to get to where you want, you can just change the thing that you want to change. If you want to build the best biomanufacturing platform, you need to get the highest control possible at the lowest possible price.
Are you making permanent genetic changes or transient genetic changes to the cells, and how does introducing these light-sensitive proteins impact the cell generally? Does it have any detrimental effects?
So you can do this either permanently or transiently, however you want, depending on your preferences.
Yes.
Scientifically, it's easier to do things permanently, because then you're working from a stable cell pool.
Yes.
But you could do it transiently if that's
Would there be a
something
regulatory factor?
Well, from a food standpoint, it's not a real concern, because these light-sensitive proteins are already eaten in very large amounts, because they're in all plants.
Yes.
And so anytime you eat a salad, you're eating a lot more light-sensitive proteins than you would consuming a Prolific burger, for example. And for pharma, which is the first application that we're going after, it's even less of a concern, because we're making therapeutic proteins using light, and the cells are not even in the product at all. The cells are just the vehicle to make your product.
Yes. You talked about the importance of precision. So where in the cell are you introducing these light-sensitive proteins, and does that vary depending on what you're trying to achieve with them?
Absolutely varies on what you're trying to achieve with them. So there's three parts to what we do. The first part is we take light-sensitive proteins and we tether them to various different targets inside the cell. The target could be any protein. And so which protein you choose depends on what do you want to achieve. So you could tune metabolism, you can activate growth factors, you can control transcription, you can control secretory capacity, whatever process you want to control, you would pick the proteins that allow you to have control over that process. The second part is hardware, so we actually build illuminators that are plug and play with existing bioreactor infrastructure. that range from super small illuminators to huge stainless steel tanks that we just demonstrated.
Do you put the illuminators inside the bioreactor, or can you? Some of them got little windows. Can you just fire light through that, or does it reach where it needs to go? Or?
There's many different ways to do it. The easiest way to do it is to not put the illuminators inside of the bioreactors, and so we've actually demonstrated in a number of different embodiments where optogenetics works really well without having any illuminators inside of the bioreactor. You either have them on the outside if it's a stainless steel tank, if it's not a stainless steel tank, and then if it is a stainless steel tank, you can build external flow-through illuminators. They're kind of like perfusion units.
Right.
They're like dialysis machines for a bioreactor, so you can just like pump it all out, pump it back in, and then you do the illumination basically in this like colon-like structure on the outside.
But it doesn't require brand new bioreactors.
It does not. No. This is all plug and play with existing bioreactor infrastructure. And then the third part of what we do is having an AI algorithm that basically has all of the sensor data coming into it, and it's taken the complexity of biology and has reduced it to maths via a series of differential equations, and then it takes all of the sensor data, it processes it, and it makes predictions. And the thing that it's predicting is what is the light pattern that I should apply at this moment in time.
Yeah, I was going to say, how do you know what the right pattern of light is to apply at any given time?
We don't. You have to figure that out.
Yes.
So the two ways to figure that out are either manual labor, which is how we've done it historically.
Yes.
We just brute force it. The better way to figure it out is to train a model that understands the system and then can make predictions on what is the best light pattern it thinks.
Yes.
And have a way of dynamically reading what's going on. So we've actually built systems like this which you can do online measurements every second of what's happening, and you can feed all of that data back into the model, and the model can experiment with different light patterns.
Yes.
And then you can see, like, is it going in the direction that you want to be going?
Yes.
If not, you can adjust the light patterns again.
Yes.
And then measure again. And so this is all heading towards the first generation of truly driverless bioreactors where we won't need to have expensive humans adding expensive molecules into the bioreactors. You can just have a shared language between the bioreactors and the cells. And if you have that, then it simplifies the process dramatically.
So what's your focus, the business? Because I know you've done some work with cultivated meat, for example, but in the first instance, does it make more sense to focus on things like therapeutics? Or?
Yeah. So we grew meat with light mainly as a proof of concept to show that this was possible. Yes. Because a lot of people didn't believe that this would be possible when I started this. So it's absolutely possible. We've made over 30 meatballs grown with light where there were no growth factor, where we activated the receptor of the growth factor using light. The first application is therapeutic proteins, and the reason for that is because they're extremely expensive. You can sell them for thousands of dollars per milligram. Yes. And we found a niche in the therapeutic protein space that is quite interesting for us because it turns out that therapeutic proteins are becoming more complicated. Yes. People used to just have monoclonal antibodies, but now they are becoming bispecifics and trispecifics and multispecifics and FC fusions and cytokine fusions, and this whole space is becoming more complicated. At the same time, the existing CDMOs, which are the people that do the manufacturing, their tools have stayed largely the same.